Okay, hello everyone. Today is the 24th of October, 1 week until Halloween. I'm sure Santiago and Jorge are looking forward to Halloween. So tonight we're going to talk about pseudo-steady state flow. And what I need you to understand is you are going to have an assignment on this problem. So you need to absolutely be able to perform all of the operations that we're going to talk about tonight. Tonight we're going to talk about liquid flow. And you're going to be able to derive this particular relationship tonight. This is an intermediate relationship. This is the more final relationship. It's a lot of work, it's a lot of algebra, it's a little bit of calculus. It's not going to kill you. Why do you have to know how to be able to derive these equations, class? Who do we have in class tonight? Let's sound off. Everybody tell me who's there. One at a time. Okay? 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 All right? Okay, sounds like we've got a quorum. So why do we need to know how to derive this equation? This is the most fundamental equation in a production engineer's library. He loves this equation, or she loves this equation, the lower one. This one in particular. What does this equation tell us? It tells us that there's a relationship between average reservoir pressure which we never know, wellbore flowing pressure, which we measure, the flow rate, and then a whole bunch of other things that are constant. So if you stare at this equation long enough, what does it look like? It looks like P average minus P WF, that quantity, is equal to some constant, which we'll call B pseudo-steady state, multiplied by rate, Q. I'm going to make all this bigger so you can see it. I hate having to go through this every time. This is the production engineer's Bible. They love this equation. What does it tell you? It tells you that there's a direct relationship between average reservoir pressure, wellbore pressure, and flow rate. Now someone tell me, we're going to have to make a whole bunch of assumptions. What are the assumptions? Very good. What's another assumption? I'm going to reduce the size of this thing. Okay, so the way we do that is we say we assume a liquid. And that liquid is what? Constant viscosity and compressibility. Do we have any other assumptions? We have to assume pseudo-steady state. And we'll talk about that condition in a minute. Is there anything else? Can anyone think of anything else? Okay, well that's part of the pseudo-steady state, but we'll say a fixed boundary. I got no problem with that. It's implied in pseudo-steady state, but that's okay. I'm generous tonight. Okay. So somewhere in here we're going to have to calculate average reservoir pressure in order to do this derivation. We'll talk a bit more about that in just a minute. But this is the first time in this course that we've actually derived something that we can use. This is a critical link. Now the big question is, how many reservoirs are they that are perfectly circular with a well in the center? 0. So there's a generalized formulation that includes something called a shape factor. And the shape factor is right here. And the shape factor and the skin factor are going to end up being friends. They're linked because they're both inside of a constant. But we'll talk about that some other time. All right, you ready? That was the easy part. Now we have to derive the solution as a function of time. How do we do that? Somebody impress me. This solution and the one on the previous page, oops, sorry, they look very similar. What's the difference? How did we find out? Where does this term come from? Somebody tell me for an A in this course. What is QB times T divided by VP over CT? It's material balance. Okay? That's the material balance part of this equation. So if you have a constant rate, then this entire term is constant, correct? if we have a constant rate. If we have a constant rate, well, you get the picture. The whole thing's constant. Okay, so if that happens and we have a relationship that says that pressure during pseudo-steady state will decline linearly as a function of time. The way I typically explain this is to think about a barrel of water that is perfectly cylindrical, and we have a pump on the bottom that pumps out exactly a constant rate. What will happen to the height of the water column or to the pressure in that system? It will decline linearly. So that's exactly what this equation describes. Okay, enough philosophy lesson. Now we got to get to work. This is taken from the notes. Conceptually, everybody needs to be on the same page. The only way this works is if the pressure at all points in the reservoir changes at the same rate. That means dP dt for all R is equal to a constant. That's given by this diagram where you can see that as a function of time, the pressure changes in a parallel fashion. That's the definition of pseudo-steady state. We have a question? Do we have a question? Okay. So the first place we start is with the material balance equation. We talked about this on Tuesday. Here's the material balance equation. Sorry, we're having internet problems. Are you able to see this and hear me? Okay, excuse me for a minute, okay? I'll be right back. Sorry guys, how are we now? Is the connection better? Okay, it must have been sunspots, sorry. I'm reluctant to change anything on this computer while I'm running because I think it'll stop it. Okay. Go ahead. Okay, where was that, on this slide or the previous slide? Okay, I'm gonna, I may break the line here, but I'm gonna turn off one. Okay, well, I'm gonna turn off one of the security features that I think may be running in the background. So if I lose you, I'll reconnect. Hopefully nothing bad will happen. Can you still hear me? Okay, is everybody still with me? Okay, hopefully that straightened out part of it. Okay, so sorry, Avery, you said you did not see anything on this page? Okay, we need to turn up our volume when we talk on the thing. Okay, so over here, what I was saying is that this implies a plot of PWF versus T will be a straight line. So, yes. Hello? Hello? Hello, hello, hello. All right. Can you no longer hear me? Hello? Okay. I'm going to check the network speed real quick. We appear to have enough speed. I'm not sure what the problem is. Yeah, we've got good speed and good maintenance. Are you still hearing me? Okay. Okay, so you can hear me now. All right, I'll keep working. Okay, well, I'll keep working and you can. I'm making a recording of this as well. So essentially, during pseudo-steady state, this definition is PWF is a linear function of T. That's what this equation tells you. And in this case, the slope is only a function of volume. Okay? So now we begin to derive this. Are you still able to hear me now? Hello? Okay, I think we've lost you again. Hello? Okay. I'm going to just keep going, and then you'll have the video after the class, okay? I'm sorry for the problems. I'm not sure that it's anything that I can do anything about, so let me just continue. Okay, as I mentioned, the assumption we make is that the pressure at all points in the reservoir changes at the same rate. So the derivative of pressure with respect to time for all radii is constant, and that means that the pressure here at this initial time will change, drop, and then drop again over time. the key here is that we begin with the material balance equation for the slightly compressible liquid. We rearrange this equation and we turn in the cylindrical geometry, and we have in front of us now the definition of the material balance for this geometry system. So this is in terms of a circular geometry. We then recall that the cumulative production is the integral of flow rate, and we substitute the integral of production into this, and we take its derivative. So the derivative of cumulative production is the flow rate. We take the derivative of equation 5, and then we have equation 8. Equation 8 is our starting point. This tells us that the mass change in the system is directly proportional to the rate. That's what equation 8 tells us. Any questions? Next, we have to utilize the diffusivity equation. We have not derived the diffusivity equation yet. We will in the next lectures. For now, you have to accept that the diffusivity equation is being given to you. The diffusivity equation in this case is in radial coordinates. The assumptions for this diffusivity equation are slightly compressible liquid, constant fluid viscosity, single phase flow, gravity and capillary pressure effects are neglected, constant permeability. Great. And then last, we're going to assume horizontal radial flow, no vertical flow. So, in this case, we're going to assume, this is our big assumption, that flow rate is constant. That will be our definition that causes pseudo-steady state to occur. It is not a requirement forever, but for today, we have to start by assuming the flow rate is constant. When we do that, the pressure change as a function of time is the same at all points in the reservoir. Therefore, the pressure change with respect to time is constant and based solely on the flow rate. As it is based only on the flow rate, then we can say that we can represent this differential equation as an ordinary differential equation. Because of the assumption of a constant flow rate, which leads to a constant right-hand side, then this equation is now only a function of position. Therefore, it can be written as an ordinary differential equation. So, the next form of that ordinary differential equation is given here. In this case, we have a second order ordinary differential equation. It's linear, obviously, because of the assumptions we made that the rate is constant. Everything else in equation 11 on the right-hand side is constant, including the flow rate. Therefore, we can simply integrate equation 11 twice, and we can obtain the solution to equation 11. The first thing we'll do is define a constant of convenience. Then we'll set that constant of convenience into the differential equation. We will separate and perform an indefinite integration. Upon performing that indefinite integration, we have this expression for the gradient and we now need to determine the coefficient C1. We multiply through by 1 over R, and now we want to evaluate this term. Since the reservoir is closed, then at the outer boundary, what happens is we have a pressure change as a function of distance at RE is equal to 0. So we use that condition for equation 15. When we do that, the coefficient C1 is given by C as in cat divided by 2 RE squared. So that's our relationship so far. When we substitute that in, we have this form. So now we're looking at an expression for the gradient, which is uniquely a function of position. If we substituted the definition of RW here, then you would see that the gradient would be maximum for RW. It would be minimum for RE. Okay? So, having said that, we now multiply through by dr. We're going to separate again, and we're going to integrate now as a definite integral across the reservoir, PR to PWF, and then RW to R. Doing this, I'll jump to the end. We obtained this form. This is the starting point form. Okay? What does this form look like, class? Can anyone hear me? Hello? Okay, what does this form look like? It looks like the steady state flow equation, doesn't it? Okay, so it looks like the steady state flow equation. There's the steady state flow equation. But it's it's for pseudo-steady state, but it has a steady state form. If we assume RE is much greater than RW, then this term is eliminated. This term can also be eliminated if we're talking about small r's, and this simply becomes the same as the steady state relation. Now, we have to have an intermediate result. The intermediate result that we're going to have is the derivation of average reservoir pressure. This is the derivation of average reservoir pressure. The identity for average reservoir pressure is given here. The average reservoir pressure is defined in terms of volume. So it's the integral of pressure over the incremental volume divided by the total volume. So then we substitute in the definitions for a cylindrical reservoir. Once we've done that, we have our final definition for the volumetric average reservoir pressure in what? In a cylindrical reservoir. So now what we're going to do is we're going to solve equation 21 for the reservoir pressure, and we're going to substitute this term into here, and by doing that, we're now going to derive the average reservoir pressure relationship. This is an intermediate result. It is not something that's going to pay much value, but we have to do this. We have to create this intermediate result. So we make that substitution, and I'm not going to joke. This is some algebra and some calculus in here. You're now going to have to break it into multiple terms, spreading out each term, term by term integration. And when you do that, you're going to have this following final form. Only in the interest of time am I jumping to this following final form. That's the final form. That's the average reservoir pressure at any point as a function of the wellbore pressure. Now we have a small problem, and that problem is that there's no such thing as average reservoir pressure at any point in the reservoir. The definition of average reservoir pressure is at RE. It's the entire volume of the reservoir. So now we have to substitute RE into this relationship, and when we do that, we have this identity, we have this identity, and we have this identity. So once we make all those substitutions, again, evolving from evaluating this at average reservoir pressure, at the total volume of the system, we have equation 39. Equation 39 is the key equation in production engineering. It relates pressure and rate during pseudo-steady state. You'll notice there's no time-dependent component on this equation. That's because the time-dependent component is here. It's in average reservoir pressure. Okay? That's where the time-dependent component is. Now, so far we've summarized everything. We have our final forms. They're given here. You have equation 38, you have equation 35, and we have everything taken care of. Now, what we use this for is to make predictions of rate. So you'll assume pressure, make a prediction of rate. There's a side derivation in here that's on the pressure versus radius concept. This is not anything of interest really, except that it turns out for the circle there's an interesting little identity, and that identity is that there's a root where average reservoir pressure crosses a pressure curve, and that gives us a unique radius. And that radius tells us what the average reservoir pressure is. It's just a mathematical convenience. We don't ever use this in practice. Okay? So we can solve this, and that magic point that I was talking about is here. So the radius at which you have the average reservoir pressure is approximately 0.55 of RE. Okay? Now the last thing we're going to do in this work is we're going to convert our equation, which is not a function of time, into something that is a function of time. So now we're going to take our previous relationship, which is in terms of average reservoir pressure, and we're going to convert it into a relationship in terms of the initial reservoir pressure, which is something that we can measure and something that we can monitor. So we then use the material balance equation to relate average reservoir pressure and initial reservoir pressure. This is very simple conceptually. So our definition, as we saw earlier in this work, this is the definition of the material balance equation for the constant rate liquid case, bounded circular reservoir. Our previous result for the average reservoir pressure is here. We simply substitute these two relationships together, and we work out the algebra. And when we work out the algebra, we have this relationship. Of course, all of this is in Darcy units. So we have the pressure at any point in the reservoir, the initial pressure of the system, RE related to the pressure at any point in the reservoir, R being any point in the reservoir related to RW, and then finally we work our way down and we have this material balance time, or sorry, material balance term, my apologies, misspeaking there. There's your material balance term, and we simply write an expression for that. Now, the next thing we'll do is we'll express this at the wellbore, and that's not done here, but all you have to do is substitute this expression for the wellbore, and you have the final form, which is given here. These are the two final forms. Either one, okay? So we have either time in days or time in hours and other units as appropriate. So we have the Darcy unit case above and the field unit case below. This relates wellbore pressure to reservoir volume, time, etc. Why are we so interested in wellbore pressure? Because we can measure it. So this becomes our governing relationship for what's called pseudo-steady state analysis. Okay, so now we'll look at some plots of pseudo-steady state, and I'll tell you this came from my thesis. I generated this using a numerical model, and that model had about 1,000 cells in it. It was a radial cell model. It was exactly the same kind of thing you develop in PETI 603, and I adopted it, I optimized it, I checked it against analytical solutions, and then I generated these results. So these are liquid-like results. These are constant compressibility liquid results. And what you're looking at is these are the pressure profiles. This is the pressure profile at 1.77 hours as it progresses up. And then here we have another, and another. So you notice the progression is just like I promised you. It's sort of a successive steady state. And what we're getting here is the performance as a function of time of pressure in the reservoir. And of course, the only pressures we can actually measure are over here at the wellbore. So we would measure those pressures and make our calculations from there. These radii are the radii of investigation at that time. And you can see the nature of these radii propagating out, and they actually propagate out as the square root of time. We'll talk about that some more in a moment. So this is a constant rate case, and it's transient flow only. This is a constant pressure case. Exactly the same concept, only now what's going to happen is, recall that I told you before, the greatest gradient occurs near the wellbore. And you can see that the gradient here is huge. So these are constant pressure wellbore behavior. And you can see that as it propagates in time, you're still locked at the wellbore. But the propagation continues. Okay? Just like that. The question that probably is on everybody's mind is there pseudo-steady state for constant pressure? And the answer is sort of. And the sort of means yes. there is a regime that is like pseudo-steady state for constant wellbore pressure. That regime is very similar to pseudo-steady state. We'll see it in a moment in some plots. And what I want to convey to you is that in a practical sense, pseudo-steady state, or more appropriately, boundary-dominated flow, does exist for the constant pressure case. Now in this case, these are pressure versus time plots. There's no logarithms. This is just brute force Cartesian plots of pressure versus time. You'll notice by my indicator that these are obviously curved. This is what the actual pressure profile would look like. This comes out of the simulator. And then the next and then the next. Okay? So are these lines parallel? Someone answer. Do they look parallel? So if they look parallel, what's that mean? That means we have pseudo-steady state. So for the constant rate case, you can see that we have pseudo-steady state type behavior. Now, let's go on to the constant pressure case. What do you think is going to happen there? Are they parallel? Class, are these lines parallel? Not exactly. There's an error out here. But that error is very far out in the reservoir. Over here, for all intents and purposes, near the wellbore, it's parallel. So what happens is you have to convince yourself that for constant pressure, you still have an equivalent concept regime as pseudo-steady state. And that's what this is showing. Okay, now we'll look at some notes that I created for imagery on pressure transient test and to show distributions. These are a little bit nicer graphs. Okay, so everyone remember, this is steady state. We've already talked about this. Then we have a radius of investigation equation, which shows the square root of time propagation. And then we have the so-called full solution. Termpon, are they going to derive the full solution in this course? You bet. This equation is in the radial flow lecture. It's not fun, but it'll make a man out of you, so to speak. Sorry about that, Miss Lee, but it will definitely change your ability level. Once you've derived this equation, you will be very comfortable with your ability to derive equations. This is the radial flow case. Looking at this equation, there are multiple parts. This is the transient part. This is one of the boundary parts. This is the material balance part. And these are, these are the shape parts. It's a circle, so there really shouldn't be much of a shape effect, but there is a transition. And I guess I could also include this as part of the material balance, but this is actually a material balance term, and this term goes to 1 for large times, so it doesn't really matter. So remarking again, this is a transient term. This is a compound transient term. It goes with this. This is the material balance term, and then this is the shape or the transition term. It is not significant. Okay. So let's look at a plot of the calculated pressure as a function of radius. The lines which are propagating in this direction. These lines are all drawdown solutions. And then these are all shut-in solutions. So the pressure is building up with time. Okay? So in this case, the pressure distribution propagates this way during production, and the pressure distribution propagates vertically during shut-in. Let me ask a very simple question from these graphics. In your mind, if I produce this well to 1,000 hours, how far can I see with the buildup? How far into the reservoir? In a manner of speaking, I can only see the distance at which I produced. So the buildup typically cannot see more than the drawdown, even if they're the same time. The buildup is a mirror image of the drawdown, but if you draw down for 10 minutes and build up for 10 days, you're not going to necessarily see more of the reservoir. And you'll notice that all of the buildups retrace the final drawdown. All of them. Okay. You'll also notice that the concept of the radius of investigation, this propagation, it occurs for both the drawdown at this point and then the buildup again. The buildup points are here. 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 So you see what happens is that the buildup retraces the drawdown. Okay? As we continue, again, our concept of pseudo-steady state is a condition where the pressure change at all points in the reservoir is changing at the same rate. I realize I'm repeating myself. This is important. You need to know this. This is a key concept. When you go out into practice, if you start looking for pseudo-steady state flow in things like nanodarcy rock, you'll never see it. Okay. So that's our definition for pseudo-steady state. Again, conceptually, our definition, and then in terms of reservoir pressure, you'll see that again we have our propagating radius, or propagating distribution of pressures, where the pressure distribution is propagating in that direction. Now what's different in this case is there's an intersection, there's an intersection, there's an intersection, there's an intersection. What is the gradient at this point, class? What is the gradient here? What's the derivative of a horizontal trend, class? It's 0. So what's the gradient here? It's 0. And that's the definition of pseudo-steady state. Okay, this is a summary of all the equations we've talked about so far. These are all derived in the notes that we covered today. You will be expected to reproduce this. I'm going to change the problem slightly, but you're still going to be expected to reproduce these relationships in some form. Don't panic, all the details in the notes. Repeating from before what we saw, this is again the definition of propagation of a pressure distribution constant rate. And again, this is repeating what we saw before. You can see the definition of the radius investigation here. And again, you've seen this before. You've seen this before as well. You see the definition of the radius investigation here. The same propagation, the same extremely high gradient here that dies off. That gradient, by the way, is directly proportional to the flow rate. And then again, we see our linear plot of pressure versus radius, so we'll understand the parallel nature of these pressure distributions. You'll notice they're exactly the same shape and they're parallel. And then we also have the constant pressure case, which has this form. And again, we talked about this being approximately parallel. The last is a discussion about why we do this. Why do we study reservoir pressure trends? Well, very simply put, we cannot measure pressure in the reservoir. We can only measure pressure at the wellbore. Therefore, all of our relationships must be referenced to wellbore pressures. The argument about whether or not we're using a simple model. Is this too simple? Because it was derived for a bounded circular reservoir, blah, blah, blah. In fact, it's not too simple. It's not too simple at all. The concept, the part about being balanced based on volume, is absolutely valid. And then last but not least is a discussion about the radius of investigation. The radius of investigation is a fictitious point in the reservoir where what happens is that the logarithm of the radius of equation, the logarithm of radius equation, the line source solution, it intersects the initial reservoir pressure. So it's a fictitious point, and it represents a theoretical location of the front of the pressure distribution. Okay, do we have questions? I'm not able to hear you very well, so please either speak up or you can send me a chat or ask a question some other way. Do we have questions? Okay, let me ask you a question. If you were me, how would you give an assignment on this problem? What would you do? What would you change to make this problem suitable as an exam problem or an evaluation problem? What would you change? What did I do last year? You mean you didn't look? Can you turn your volume up? Let me turn my volume up. Okay, I'm in maximum volume now, so talk away. I have no idea what you're talking about. Okay, well, here's the exams I gave last year. Can you see it now? Okay, in this case, this is going to be a derivation problem. You'll see this, something like that. And then this is another problem. Don't worry about that one. Don't worry about that one. Don't worry about that one. Well, I'm not going to give you the same problem. Okay, this is the one you need to worry about. Okay, so now, what am I going to do? I'm going to ask you to derive this relationship in terms of pressure squared. How would you derive the equation in terms of pressure squared? You'd use the diffusivity equation in terms of pressure squared, which is here. You'd use the material balance equation, which is in terms of P over Z. Uh-oh. So we're going to have to make some concession to convert P over Z to pressure squared. Okay, well, you'll see this again soon. I won't take the surprise away from you. All right, so everyone have a good weekend. So I'm going to try to do that and to cause so much pain that I hear the collective scream from here. All right, I will be with you on Wednesday, Thursday, and Friday nights. Don't forget about that. Really? Well, I made a mistake. Let me check and see. You know, this is why you shouldn't send emails late at night. You know, sometimes I want to reach through the internet and strangle you. Yes, you are bad. You made me a little crazy there. All right, so everything I do from now until the time I see you is going to be to try to get this straightened out, right? The assignment. And if we have any questions, we can go over it. Yes, I see. Tuesday, you're in charge. Wednesday, Thursday, Friday, I'm in charge. Okay, and again, guys, I'm sorry, but on Tuesday the 5th, Thursday the 7th, Tuesday the 12th, Thursday the 14th, I'm going to have to do WMV. I'll have to record it and mount it. I am not going to fall behind. I'm going to stay up with you, but I'm going to be in places where I don't know what the internet's going to be. Okay, let me be honest. It should be better than this, but I don't know exactly what my timing's going to be. And then after that, you see what we go back to. All right, so I will get you something over the weekend, and please feel the love. All right, everyone. Thanks for your patience with me, and we will talk soon. Okay, bye-bye, everyone. Thanks for your patience again.